All right, let's dive right in. Today, we're going to get to the heart of the climate challenge. We're going to peel back the layers and really look at the massive scale of the problem, some of the amazing tech being built to fix it, and the hidden dangers that have scientists truly worried.
So, to really wrap our heads around what we're up against, we have to start with a number. It's a number so big it feels fake, but it's the actual weight of the carbon dioxide we're putting out there every year. Any ideas what it might be?
The number is 37 gigatons. And just to be clear, that's 37 billion metric tons of CO2 that we are pumping into our atmosphere every single year. It's an almost impossible number to picture, so let's try and make it real.
Okay, look at this. Picture the National Mall in Washington, D.C. Now, imagine a pile of coal sitting on it that's 10 times taller than the Washington Monument. That massive, unbelievable pile, that's 1 gigaton. And we emit the equivalent of 37 of those every year.
And here's the real kicker. This isn't a problem that just resets on January 1st. Nope. Pretty much everything we put up there stays up there, trapping heat for hundreds, even thousands of years. We're not just dealing with this year's emissions. We're dealing with a pile that's been growing since the Industrial Revolution.
So when you're faced with a problem that big, it's no surprise that people are asking, can we just, engineer our way out of this? Innovators are building some incredible tools to do just that. But the real question is, can these sci-fi solutions actually work on a global scale?
One of the big ideas is something called direct air capture, or DAC. You can think of it like a giant vacuum cleaner for the sky. It's pretty straightforward, really. You have these massive fans that suck in just normal air. Then the air passes through a special chemical filter that's designed to grab only the CO2 molecules. Finally, you add some heat, and that releases the CO2 in a pure, concentrated form.
But, and this is a huge but, we have to talk about scale. Right now, if you took all the DAC plants operating on the entire planet and added them up, they capture a few thousand tons of CO2 a year. Now remember that other number? 37 billion tons? When you see them side by side, you get it. The challenge isn't just the technology, it's scaling it up massively.
So let's say we capture all this CO2. What do we do with it? Well, this is where it gets really cool. In places like Iceland, they're injecting it deep into volcanic rock. And get this, it actually turns back into solid stone in just a couple of years. Other people are working on recycling it into carbon-neutral jet fuel, or even using it to make things like concrete.
And this brings us to a really critical difference we have to understand. Making jet fuel from captured CO2, that's called carbon neutral, right? The carbon came from the air, you use it, and it goes back into the air. It's a closed loop, net zero. But turning it into stone, that's negative emissions. You've taken carbon out of the cycle and locked it away for good. That's the real game changer.
Look, all this technology is amazing, but it's not going to be ready to solve the whole problem tomorrow. So it kind of begs the question, what happens as we keep pushing the system harder and harder in the meantime? What's the thing that scientists are really losing sleep over? And that brings us to one of the most sobering and, frankly, scariest concepts in climate science, tipping points. These are the thresholds in the Earth's systems where things stop changing gradually and start changing suddenly, massively, and maybe forever.
So what is a tipping point? Well, it's exactly what it sounds like. It's that critical moment where one tiny little extra push doesn't just nudge a system. It sends it spiraling into a totally new state. And once it tips, getting it back is incredibly hard, if not impossible.
Probably the best analogy for it is this. Imagine global warming is just slowly pushing a glass of water across a tabletop. Every little bit of warming is another tiny nudge. For a while, you don't notice much difference. But once that glass gets to the edge, the next tiny nudge doesn't just move it a little bit more. It goes over. And the result is a sudden, messy crash. You can't unspill the water.
And when scientists look around the planet, they see several of these glasses sitting dangerously close to the edge of the table. We're talking about things like the total collapse of the Greenland ice sheet, the Amazon rainforest turning into a dry savanna, or a critical ocean current that controls weather for half the world just shutting down.
And what's worse, these systems are all connected. They don't exist in a vacuum. The meltwater from Greenland could mess with the Atlantic currents, which could then change rainfall patterns over the Amazon. It's like a row of dominoes. One goes, and it could trigger a cascade across the entire globe.
So, wow. I mean, the stakes could not be higher. Which leads to the ultimate question, doesn't it? If we know this, if we see the risks, why is it so profoundly difficult for us to get our act together?
Well, the answer might not be out there in the atmosphere. It might be in here. And that brings us to the final piece of the puzzle. Us, what you could call the human superorganism. Because maybe the core of the problem isn't just the CO2. It's the profound mismatch between our ancient brains and the world we've built.
You see, our brains are basically running on ancient software. We evolved over millions of years to be fantastic at responding to immediate, visible dangers. The tiger in the bushes. Our fight-or-flight response is perfect for that. But an invisible gas that builds up slowly over decades, our brain just doesn't register that with the same level of panic. It's a complete evolutionary mismatch.
And this little psychological quirk is what powers our entire global machine. Our civilization runs on what you could call fossil slaves. To put it in perspective, the energy in just one barrel of oil is equal to about 4.5 years of hard human labor. And a whopping 80% of our global energy comes from these tireless but polluting servants.
This quote just nails the dilemma perfectly. For almost all of human history, survival was about the here and now. Worrying about the distant future was a luxury you just couldn't afford when you were worried about your next meal. That short-term bias is literally baked into us.
So, where does that leave us? In the end, it feels like the technology is solvable. The science is clear. The greatest challenge isn't really out there. It's in here. The ultimate tipping point might just be a human one. The question is, can we use our conscious, modern minds to override our ancient wiring? Can we learn to think differently before it's too late?